spin this little plastic top, and within a few seconds, something impossible happens. The whole thing flips itself upside down, standing on its tiny stem, spinning the same direction, center of mass higher than where it started. Pauli and Bohr watched one of these for an hour at the opening of Bohr Institute in 1954, two of the greatest physicists of the 20th century, mesmerized by a child's toy. Why does it flip? The toy is dead simple. It's a hollowed-out hemisphere, smooth and round on one side, with a thin stem sticking out the top. When you set on the round side and spin it like a normal top, it spins for a moment, looking ordinary. And then, against everything your physics intuition is screaming, it starts to wobble, tilt, and slowly invert. Here's why it feels impossible. The center of mass actually rises during the flip. The top spins energy, lifting itself against gravity while spinning. Things should fall to lower energy. They don't usually crawl uphill on their own. So what is feeding the climb? The answer is the most important word in classical mechanics: friction. At the contact point between the hemisphere and the table, there's sliding friction. Because the spin axis isn't perfectly vertical, the contact point doesn't just drag straight back, it drags sideways too. That sideways drag creates a torque perpendicular to the spin axis that slowly tips the angular momentum vector. The vector rotates, and the body has to rotate with it. The full equation of motion is just Newton's law for angular momentum. Tau equals dl by dt. The friction torque, tau, points off axis. So the angular momentum vector, L, slowly precesses, tipping further from vertical until the top is upside down. Once it's standing on the stem, the spin axis is vertical again. No more lateral friction torque. Equilibrium, spinning peacefully on its head. Why is the inverted state stable? Because under continuous friction, energy keeps dissipating. The system slides toward the lowest energy state consistent with the conserved angular momentum. And for this geometry, that lowest state is stem up, not stem down. Friction doesn't just oppose motion. It selects the resting configuration the laws of physics prefer. Same physics is everywhere. Spinning planets gradually align their rotation axes with their orbital plane. Atomic magnetic moments precess in MRI machines and align with the field. Gyroscopes used in submarine and spacecraft navigation depend on this exact dance between angular momentum and applied torque. The tip-top is the cleanest desktop demo of laws that govern everything from quantum spins to the rotation of galaxies. Friction isn't the enemy of motion. Sometimes, friction is the architect. It steals energy in tiny bites, and what remains after the dissipation is the configuration the universe happens to prefer. Spinning quietly, on a stem, defying nothing, obeying everything. If this surprised you, hit like and subscribe. Counterintuitive physics every week.